So I'd like to describe a remarkable result called Frobenius divisibility. It says the following: if I have an irreducible representation of a finite group, and if that dimension has a finite dimension d, and n is the order of the group, then the dimension of the representation divides the order of the group. So the dimension of irreducibles divides the order of the group. That's a remarkable result. It reminds you a little bit of things like Lagrange's theorem. However, it's much harder to prove. So I'm going to describe the ideas of the proof, and it's a little bit involved, so this will take a little time. So the main idea of the proof is going to involve the following. So let's fix our irreducible representation of dimension d. Let's define an operator on V, which I'll call Tg. It's defined for every element of the group. It's defined to be the sum of the operators phi x, where x runs over elements of the conjugacy class of G. So that's a linear map from V to V. In fact, it's a morphism from phi to itself. So that's just a straightforward verification. You check that for any element A in the group, you have that formula, and we've done almost exactly that calculation before. Now, because phi is actually irreducible, Schur's lemma tells you that Tg is some multiple of the identity, because it's a morphism from phi to itself. And we actually have a formula for lambda g. It's the size of the conjugacy class of G divided by the dimension of the representation times the value of the character at the element G. Where do you get this? It's because you can take the trace of this operator. On the one hand, from the formula, it's the size of the conjugacy class times the character. On the other hand, it's a multiple of the identity, so it's that number times the dimension of the representation. Here's a variant of this construction. Let's let S be the following operator. I'm going to take the sum over all elements of the group of the value of the character of the representation at G inverse times phi G. So that's an operator. Now, if you think about this, you can write this as a sum over conjugacy classes. So I'll use this notation. X sub I is a set of representatives of conjugacy classes of G. And so I'll take chi evaluated at xi inverse times txi. So I've just grouped together everything that's in the same conjugacy class. Again, I could take the trace of S. On the left-hand side, I'll get a sum over elements of the group of chi of G inverse times, well, the trace of phi G is chi G. Well, that's basically something that fits in an orthogonality relation. If I put in the order of the group, and I remember that this thing is really chi G bar, this actually works out to n times chi paired with chi. But it's an irreducible representation, so the orthogonality relation says that n. On the other hand, I also have the right-hand side, so that's going to be a sum over these representatives, that character value, times the trace of txi, which remember is some multiple of the identity. So the number pulls out, and we get the dimension of the vector space as the trace of identity. So these are equal. So let's turn that into a single formula. N over D equals the sum over these set of representatives of this expression. So there's the formula. So that's a bit promising. It's an interesting formula. The right-hand side is just some complex number, but the left-hand side is a rational number. We actually want to show that this is an integer and not just a rational number. So I'll prove that the left-hand side is actually an integer by proving something about the right-hand side, which seems a little non-intuitive because the right-hand side is more complicated. So what I'll do is I'll identify a set that the right-hand side is in. So let's let R be the following subgroup of the complex numbers viewed as a group under addition generated by the set of elements. Here's the set. I'm going to take zeta to the I times lambda sub g. Here, I is an integer running from 0 up to n, and g is an element of the group. And what's zeta? Zeta is e the 2 pi I over n. N, remember, is the order of the group still. I claim that this funny expression is in R. Of course, that funny expression is none other than n over d, so I'm really showing that n over d is in R. Well, there's a lambda. What about that thing? That's the character. The character of an element of a group is a trace of phi g. So without loss of generality, we can assume that phi is a matrix representation. We have to do that to compute the trace. And we know that this thing is going to be diagonalizable. In fact, the order of g, and therefore the order of phi g, divides the order of the group, which is n, so the eigenvalues have to be nth roots of unity. So the matrix will be similar to something like that, and so the trace will be a sum of those powers. And if I take that and multiply that by a lambda, that's a sum of these expressions. So that's the proof that that number is in R. Okay. So the rest of the proof amounts to the following claim. This subgroup R intersected with the rationals is the integers. Now, this expression n over d, it's obviously a rational number. Because of this expression, it's in R, so it's in the intersection, and that will imply that n divides d. So that's what I owe you. That's going to be the proof of this statement.